Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. So we are very pleased today of having Pierre Pinson, who is the chair of Data-Centric Design Engineering at Imperial College London at the Dyson School of Design Engineering. He is also a chief scientist of Half-Space, which is a data analytics and AI company. Pierre is the EEE fellow in class of 2020. He's also an Informs member and an Institute of Forecasting director. He has been on the highly cited research list of the Clarivate in 2019, 2020, and 2021. In the crossfield category for the numerous high-impact works that he has on statistics, meteorology, economics, and power and energy engineering. In terms of the areas of application, Pierre is mainly focused on energy and meteorology, also having looked at shipping and logistics, as well as business analytics broadly. So some of the works he's known for include probabilistic forecasting, forecast verification, peer-to-peer and community-based markets, coordination of energy markets, collaborative market-based analytics, etc. And I would like to mention that very recently, Pierre and colleagues received the 2024 France Edelman Award that recognizes and rewards outstanding example of operations research, management science, and advanced analytics. I could go on and on, but I think you realize that we have a very renowned speaker today. So we would like to thank you for your precious time, and the floor is yours. And for the audience, please remember that if you have a very urgent question, put it in the chat and I will pay an eye to the chat. And if not, you will have time for questions at the very end. Thank you so much.
Thanks very much. Can you see my screen?
Yes, we do.
Yes. So the slides with the beautiful new logo of Imperial College at the top right. So thanks very much, Dolores, for the introduction, and thanks for having me here today. It's a pleasure to contribute to what I understood is the last of this online discussions. I want to talk about online learning and decision making. It's something I've been doing for more than 20 years. I started originally working with forecasting for renewables. But seriously, forecasting is not so exciting if we don't try to connect it to some decision-making problem. And now, I mean, there's a lot of activity in that field. People are developing new forecasting methods. People are trying to do prescriptive analytics so that we directly make decisions based on contextual variables. So I want to discuss a bit of that today. But also I want to drift towards more data-driven decision-making when we don't trust the forecast fully. So that's where we're going to use a distributionally robust optimization for trading. Before I get started, I should say thank you to some people. Here there's some contribution from some colleagues. So Miguel was a guest from Malaga for some months with us at DTU. And then we worked also with my colleague Jalal Kazempour on some of the work that I mentioned here. And I see someone from Malaga is joining, Salvador Pineda. So there's a connection. So that's for today. And I should say thank you also to EU for providing some funds for this research. The project Smart Forest partly contributed with funds, but you also did this work, without any funding, just as free research. Good. So the agenda for today is I want to give a very quick introduction to renewables in electricity markets. So I'll use wind as an example, but it could be the same with some other type of renewables. Maybe some of you are very familiar with the topic. Some of you are not so familiar. So I just thought we should spend 1 or 2 slides to make sure that we all on par. Then we'll go to online learning and decision making. So that's where I will discuss some of the work we did with colleagues. And then I'll zoom in on generalization of the newsvendor problem, which is at the core of all these decision problems in electricity market. And I'll go towards distributionally robust version. So that's the agenda, and we'll try to make it 35 minutes or so that we have time for discussion afterwards. And then I know that Dolores wants to have some time also for some closing session. Good. So renewables participate in electricity markets. I think we've all seen some works here and there with renewables in electricity market. There are also some books on the topic that cover different aspects of stochastic optimization, pricing, market design, etc. When we think of renewables participating in electricity markets, typically, if we look at the simplest approach, but that is very, very general, that is a newsvendor problem. And newsvendor problem is actually one of the most classical problem in stochastic optimization. So I think it's difficult to have any course in decision making under uncertainty or in stochastic optimization where you would not discuss the newsvendor problem, even as a starting point, right? That's one of the most basic problems. The thing that's also interesting with this, that there's been quite a lot of work, and maybe it's been trendy over the last few years to focus on prescriptive analytics, this big data newsvendor problem and the likes. But actually, the newsvendor was something like that from the start. People say it's stochastic optimization, but some other people say it's statistical decision theory. And in the late 50s or even early 50s, people were actually showing for this kind of problem, we can actually directly learn the optimal decision from data. And then you could have any kind of model to do that. And also it has a strong link to say, if I have to do decision making under uncertainty, I can model my uncertainty with some kind of distribution, and I know the optimal quantile that I would use as my optimal decision. It's actually also even older than that. You can see here a reference to Edgeworth. Edgeworth was the first one to introduce this problem 130 years ago, almost. And the idea is very simple with this problem. It's an expected utility maximization problem where there's no risk aversion in the basic version. We have a one-shot possibility to decide on a quantity of interest. So when renewables go in electricity market, you have to think of it as your bids. It's the energy generation that you want to offer and get scheduled with. The outcome is uncertain. So for renewables in electricity market, it's quite clear. You have to bid in advance. So you're not 100% sure how much you're going to produce because perfect forecasts don't exist. In the basic version of newsvendor problems, and we'll get to that because this is not the case here with renewables in electricity market. In the basic version, you should know what are the marginal profit and loss. And for us in the electricity market, that would be instead the penalties for being long or being short in the market. So in the newsvendor problem, you should know about these penalties, but actually for the electricity market case, we don't know. And obviously we have an expected utility maximization, so we want to maximize expected profits. There's no risk consideration here. All right, so if we were to write it more mathematically, this would be something like this. Think of it as today at noon, you want to trade for tomorrow. The market is cleared around noon in most areas in Europe. And then the time schedule we consider is tomorrow, midnight to midnight. In some countries, the market time units are hourly. So you have 24 blocks you need to offer for based on your forecast. In the UK, for instance, it's half hourly. So you have 48 blocks. Most likely in the future, it's going to be harmonized all over Europe. So you will have blocks of 30 minutes, most likely, but it could be also 15 minutes, maybe in the future. So whenever a renewable energy producer or someone who manages the portfolio is offering in these markets, they have to consider their forecast for generation, power, energy generation for each and every block the following day. But they also need to think of the market prices. The actual market prices are not so important. As for many trading applications, it's the spread between prices that is important. But this spread is defined based on the day-ahead price. So that would be the price when you're cleared in the day-ahead market. And with the real-time prices, right? The regulation prices, if you overproduce or if you underproduce. So based on that, we define two kinds of spreads. There's one spread, which is what's going to happen if you overproduce, and that's the overage penalty. And one spread, which is what happens if you underproduce, and that's the underage penalty. All right. So for each and every program time unit, we can write the revenue of the producer as what you see here in the middle. It's been already rearranged, right? So that it's easier to play with. This omega is the random variable for energy generation, okay? The pi S, pi O, and pi U are the dead prices and the two penalties. And Y is your decision, okay? So the first term here in the revenue, it's pi S times omega. At the time of making a decision, you have a random variable here, but eventually it's fatal, right? It's your decision doesn't affect this term. So whenever we look after at the optimal decision you can make, actually this term can be removed because we cannot really do anything with it. So the only terms we care about, they are the two following terms. It's pi O times omega minus Y, and we take only the positive parts because this penalty only applies if you overproduce. And then you have the other one for when you underproduce, and it only applies when you underproduce, okay? Good, so based on this revenue with this random variable there, we want to maximize expected utility, and that's the optimization problem we have just below. And we know that textbook material, I have nothing new here for you. We know that the optimal decision we can make is one specific quantile of the predictive distribution for energy generation. And the nominal level of this quantile is directly given by the asymmetry of the two penalties. So you have pi O at the top, and you have the sum of pi O and pi U at the bottom. So think of it, if pi O is equal to 0, that means there's no penalty for overproducing, so producing more in real time than what you've been scheduled for. So the optimal quantile to bid in the market is the quantile with nominal level 0, because you really don't mind if you produce more than what you bid. And the opposite, if pi O is equal to 1, you place yourself at the maximum potential generation you believe you could get to. And then it's because you believe you cannot be penalized for producing less than your bid. Typically, for actual application in electricity market, we know that the optimal quantile oscillates around 0.5. But in certain markets, in certain periods of the year, it might be, between 0.5 and 1, and some other period is between 0 and 0.5. So, sometimes it's better to try to, let's say, over-predict in a general sense, and some of the time it's better to under-predict. Good. There's one assumption I didn't mention so far, is that if we think of renewables in electricity market and using this kind of approach, we make the assumption that wind is a price taker, or renewables in general. Being a price taker, that means that whenever you make a decision and there's an outcome from the market, your decision has not impacted the market outcome. So is this realistic? I would say 20 years ago when people started doing research on this topic, yes, for sure. I don't see many wind farms that could really impact market outcome. But as of today, maybe it's a bit less realistic. Still, that's a classical assumption that many of us use. If you were to think of being a price maker in the market, there are different works that look into that. I'm being a bit selfish here because I'm showing works where I was a co-author. There are also works by other colleagues where they look at different angle. So there are some works, for instance, by Baringo and Conejo, where they also look at pull strategy of a price maker wind power producer. But here, just what I wanted to show you is that as of today, if you offer with wind or with solar energy in electricity markets, there's two effects we need to think of. Maybe we're a price maker directly with our assets. So think of a large offshore wind farm. Today, a large offshore wind farm in a country like Denmark could produce several percent, maybe 5 to 10% in extreme condition of the overall energy being consumed at a given time. So I think it's difficult to think that you're a price taker in all occasions. But then also it can be through population effects, because most likely There are large groups of wind farms that are exposed to the same kind of weather condition. They have quite similar weather forecasts as input. They may use quite similar strategy for participating in electricity market. So at the end of the day, maybe as a single asset or an asset manager, you think you're not a price maker, but as a group, you are a price maker. And so there you could also adapt your trading strategies to understand what would be the joint effect of everybody on the market. When we think of these price maker issues, you could be a price maker on the day at price. So your decision is going to impact the day at price. You can be a price maker because you affect the system state. So, you know, the fact that there's too much energy or not enough energy in the system may be due to your decision. It can be also on the penalties, the spread in the market, etc., etc. So it is something that is not really well studied, and I'm not going to dig into that much more, but just I thought it's important to mention it here. So now I would like to discuss this problem of online learning and decision making. We're going to do that without equation because we'll have a lot of equations after for the distributionally robust versions. But still, I wanted to tell how we can use online learning and decision making in a quite straightforward manners for this kind of news vendor problem for wind and electricity markets. So we're going to call it the Munoz-Pinson-Kazempur approach because there's a paper that was published last year in the computational management science where we describe this idea. I have to say that a lot of what is in this paper is actually stuff that we knew from different fields, right? So I know that quite a few people, for instance, these days, have shown, you know, within a prescriptive analytics framework, we can use some kind of decision rules, right? Linear decision rules, or we can use a kernel trick so that they become nonlinear. And then we make these decision rules a function of contextual variables, and we're going to learn the parameters based on data so that after we can make optimal decision when we have new conditions, right? That's not from me, that's not from us, but it's something that is used more and more around us. The thing here, we have a specific loss function, right? We have this news vendor loss function due to this asymmetry of penalties. And so somehow we generalize the learning problem with the news vendor loss. And so that we can learn online, also we use a time varying loss function with a forgetting factor. So then that means that whenever some new data is coming, the loss function is different and we adapt to conditions, right? So it can be the seasons, it can be, for instance, a price making behavior that can be varying during periods, etc., etc. We can just adapt to that. Technically, whenever we want to update the parameter values for these decision rules, because we have a loss function that is not, you know, like if you had a quadratic loss function, you can calculate gradients at any point. But here, since it's not the same type of loss function, it's a bit more tricky. So there are two ways. Either we can actually make it strictly convex, this loss function, and then we can calculate gradients, or we can use a subgradient based approach so that we can still update the parameters of the decision rules, whatever happens. And finally, there's a forgetting factor in this kind of approach that we optimize. And like for many other data-driven optimization approaches, we can use cross-validation, or like you use for machine learning also, right? So think of it as a nice framework to consider if you want to look more generally at decision problems for renewables and electricity market, and also accepting that it's going to be time varying. But now I want to generalize this problem so that we can robustify it, right? I want to use distributionally robust optimization so that also in a data-driven manner, we accept the fact that maybe we don't fully trust the forecast we are working with. So why I want to do that, I insisted when I introduced the news vendor problem, this spread, these penalties in the electricity market, they are not known, okay? But in the way the electricity market is set up, we know that only one of the sides is going to be active. You know, the market is going to be long or short, and you as a producer, either you produce too much or you produce too little. So eventually, what we're exposed to is some kind of Bernoulli variable with a chance of success that is given by this parameter, this asymmetry of the spread, pi O over pi O plus pi U, okay? So we can rewrite the newsvendor problem that we had before, where we had to assume that the penalties were known, the penalties, the overage and underage penalty. And instead we say, okay, we have a newsvendor problem with a Bernoulli variable, and this chance of success of the Bernoulli variable, maybe it's known, maybe it's not, okay? So that's what I describe here. So we can write this Bernoulli newsvendor problem. It looks very similar to the original newsvendor problem, except that you can see here in terms of the opportunity cost, we have this S and 1 minus S in front of the two terms for overproduction and underproduction. Remember that a little plus here on the bottom right of the parenthesis means that we only take the positive part, but it's pretty much the same as what we had before, just that we have a Bernoulli random variable. And what is nice with that is that under the same condition as for the original newsvendor problem, so if we do expected utility maximization as a price taker, then we have the same solution as for the newsvendor problem, except that the optimal quantile is given by the chance of success for this Bernoulli random variable. But that's very consistent with the results we know from before. Good. The reason why I wanted to do that is that now I have two types of uncertainty in my newsvendor problem. I have the uncertainty from the renewable energy production, and typically we have a predictive CDF, we have a probabilistic forecast for that. And I have this uncertainty from the asymmetry in the market penalties, right? And that's this Bernoulli random variable that is there to model that. So I want to do some kind of distributionally robust optimization for these two types of variables. They're quite different because for the renewable energy generation, if I have a predictive CDF, it can be non-parametric, right? I just have a CDF to play with. And at the opposite, a Bernoulli random variable is like the easiest random variable to play with. There's just two potential outcomes with this chance of success. So we'll discuss it. It's very easy to robustify or to use distributionally robust optimization for that. Good. So the problem setup is that in all cases, we'll have some probabilistic forecast for this two type of variables as inputs. So omega, the renewable energy generation, and that's the kind of plot you have here on the left. It's very common today. Yeah, there's so many methods to produce a probabilistic forecast for renewable energy generation, especially for wind energy. And we can have a predictive CDF for each and every market time unit when we participate in the electricity market. And then the second variable we care about is this Bernoulli random variable S. And similarly, even though it's quite more difficult to do probabilistic forecasting for market quantities, there are quite a few papers that propose methods, to predict the state of the market, to predict the penalties, to predict the volume of imbalances. So from this kind of forecast, you can actually deduce some forecasts for the Bernoulli random variable that we care about. Okay, it's just a chance of success that we have to predict. So now we want to use distributionally robust optimization for these two types of variables. For the first type of variable, so that's omega, the renewable energy generation, the solution is not from me. It's something that I found from this paper of Hu et al. 2021. It's available on arXiv. And they propose to build some ambiguity sets for a variable like our omega variable here. Their application is not electricity markets at all, but they start from the same kind of setup where they have ambiguity on the variable omega. So here, given a Bernoulli random variable, but we put it aside, we don't try to do distributionally robust optimization on that for now. We have an estimated or predicted chance of success tau hat, okay? And we want to play with the predictive CDF for omega. So we need to build an ambiguity set, a ball around this predictive CDF, and this ball has a radius of rho. And then when we've done that, I think many of you have worked with distribution robust optimization. We have a min-max type problem. So we want to find the worst case scenario for all the predictive CDF within the ball. And then we minimize in expectation for this worst case scenario, right? So how do we define this ball? Because that's often the tricky part to define the ambiguity set. So the proposal, which I have adapted, I didn't directly take the proposal from these people, but it's a very pragmatic approach, which is quite suited here. You use some concept of first order stochastic dominance. And by doing that, that means that if you see here the plot on the right, in black, you would have the original predictive CDF that you get from your forecasting method. And using first order stochastic dominance, you say, okay, we could deform this predictive CDF so that on the lower side, I could push it so that, you know, you go to the corner, so 0, 1, and going up here as a Dirac on 1. And on the upper side, you do the opposite. You could deform your predictive CDF so that it goes all the other way until you have a Dirac at 0, okay? And then rho is controlling how, let's say, how far you allow deformation from this original predictive CDF. You see here 2 examples. In blue, it's with a small rho, it's 0.2, and in green, it's with a larger rho, it's 0.7. And then when rho would be 1, you would have a Dirac on 0 on one side and a Dirac on 1 on the other side. So this is something that I propose based on the original idea by Fu et al. And this is described in the papers that are linked to this talk. Good. Now, the very nice idea I find from Fu et al. Is that they showed how we could get the worst case distribution from this ambiguity set and what would be then the optimal bit or the optimal quantile, you could say, within this distributionally robust framework. So if you look at this plot here, which is directly reproduced from their work, it's not from me, you see they say we have these 2 deformation that define the extremes of the ball. And then if you think of the worst case, that would be the upper one up to QU here. So it's when you reach on the y-axis the optimal quantile of the classical newsvendor problem. When you're left of that, you're on the top side. Then you go through the ball. And then after that, it's the bottom one, which is the worst case. So there's a proof in their paper. It's quite neat, actually. And so then that means that in a distributionally robust framework, our optimal decision is somewhere on this flat line that is crossing from one side to the other of the ball, all right? And they show, and I could also verify it, I could rewrite the proof. They show that the optimal decision that you would make based on this ambiguity set, so it's first order stochastic dominance, if you have a given chance of success forecast or estimated tau hat, this is the optimal decision to make, right? So you are within this line at the level on the y-axis of tau hat, and you find the right point along this line where there's a weight given based on tau hat, right? So if tau hat is very small, you're completely on one side. And if tau hat is equal to 1, you're completely on the other side, okay? Good. What is nice and what you want to have is that if you increase a lot the value of rho, then you should find the robust optimization limiting case. And here, that is really the case. If you have sufficiently large value of rho, the ball makes that actually it's like saying, you know, I have a uniform distribution. I have no real information about renewable energy production. And so then the robust solution would be to take the optimal quantile from a uniform distribution. And so that's the solution you have here. The optimal decision is tau hat, which is the optimal quantile of a uniform distribution. So that's what we expect. That's the robust limiting case. Now, if we have, which I think is more interesting, you have ambiguity about the Bernoulli random variable. We assume that we just stick to the distribution, the predictive density for renewable energy generation, and we only focus on ambiguity for the Bernoulli random variable. So we have an estimated or predicted chance of success, and we want to build a ball around that, right? And then we have the same min-max optimization problem to solve to have a distributionally robust optimal decision. So how do we build a ball for a Bernoulli random variable? As I mentioned earlier, a Bernoulli random variable is pretty much the simplest kind of random variable we can work with. And whatever we need to characterize the random variable is the chance of success tau. So an ambiguity set, it's an uncertainty on tau, right? So if we have an interval around tau hat, so you go plus minus epsilon around tau hat, that's a ball that defines the ambiguity set. We can do it in different ways because you can see that if you use an epsilon plus minus, it may go out of the range 0 to 1, and you may want to think there's some kind of asymmetry as you get closer to the bounds. So we've looked into two types of ambiguity set. One that would be uniform, that's the top one, and one that would be level adjusted when you have some kind of asymmetry as you get closer to the bounds. All right, good. So now let me show you the intuition for the final results in terms of the distributionally robust optimal participation strategy. You have here three cases, and you have to think in terms of worst case over the ball, right? So there are three, for each cases, there are three lines we need to look at. What would be the expected utility? So think of it here, there's an example distribution, predictive CDF for renewable energy, and we integrate, we have the expected utility for different level of the decision Y. So that's why here on the x-axis, you have the decision Y, and on the y-axis, you have the expected, well, here it's not a utility, it's a cost, right? You want to minimize it. It's a penalty, expected penalty. So we have these three cases, and as I said, we have the blue line where it's the expected utility if we use tau hat. The green one is tau over bar, so that's one side of the ball, and then the last one in black, dash black, it's tau under bar, and it's the other side of the ball, right? If you focus, for instance, on the left, you can see that the worst case scenario where you're left of the point y equals 0.25, the worst case is the green line. And when you're on the right of this point 0.25, the worst case is the black line, right? And it's actually happening when the minimum for all these expected utility curves are on the same side of their crossing point, right? And so in that case, we know that the minimum of the worst case is going to be for this green line. So it's tau over bar. And we just take the minimum over this expected utility, and that's our distributionally robust bit. On the very right plot, you have the opposite situation. On the right of the point 0.25, you see the three optimum value for these three expected utility curve. They're all on the same side of the crossing points. But there, the worst case scenario is the black curve for tau under bar, and our distributionally robust optimum is the optimum of this curve here, the black curve, the minimum here. And then we have the one in between, where it's a case where actually the minimum for these three curves are not all on the same side of the crossing point. And in that case, the one that is really the minimum is going to be exactly where they cross, right? That's the solution where the expected utility are not all aligned, if you want. And you can generalize that. It's proven mathematically in the paper, so that eventually we have, it doesn't read very well, but it's really summarizing these three cases, right? We have to check where these optima are for the three expected utility curve. And then depending on the case, we know which one to pick. So that's very nice and useful. Again, we have a very nice following limiting robust case. If you increase epsilon to the maximum, right, which should be 1, if you normalize the ball radius, the solution here of the distribution robust Bernoulli newsvendor problem, it converges to the expected robust solution, which is if you have no information about the penalties in the electricity market, the robust bid would be to beat the conditional expectation from the probabilistic forecast for renewable energy generation. So it's nice that we end up with this because it should be consistent, right? So let me give you some quick examples, and then we'll close in maximum 5 minutes. So we did a lot of Monte Carlo simulation to retrieve what we expect to see for distributionally robust optimization, which is that when the ball radius is small, is equal to 0, we should start here. So it's the left side of the plot. That's the case where there's no ambiguity. As we increase epsilon and we accept there is some kind of ambiguity, we should do better. So here you can see all the curves, the blue and the red, they go lower. And then as we increase epsilon to the maximum, which is 1, we should converge to the robust solution. And you see here somehow we have a sweet spot, right? There's an optimal value of epsilon, and that's the point of doing distributionally robust optimization. We believe we can find this sweet spot so that we get something that is better than not having the ambiguity and going robust. You have 3 flat curves here in black. One is the oracle, so that's the one at the bottom. It's the best we could do if we had perfect information. One is the classical Bernoulli newsvendor problem, and that should be the starting point, actually, when epsilon is equal to 0. And the last one is the robust one, and you see that's where they converge when epsilon tends to 1. So there's some technicalities here. Because of the way I've defined the problem, it doesn't exactly start where you expect it to start and not exactly end where it expects to end, but it's due to some details on how we play with the ball radius. So you can see it behave as it should. So we did some experiments. I'm going to skip that. We did some experiments with some real world data from France. We used some periods for cross-validation, for optimizing some models, for finding the optimal ball radius, etc. And then we used 600 days for genuine out-of-sample evaluation. So that's nearly 2 years. On the right here, the plot is the delta regret. So it's how much better we do than the classical newsvendor problem cumulatively over time, over the days. And on the left in the table, that's the kind of revenue we get per megawatt hour actually produced with the different approach. So you have the oracle, so that's the best we could ever do if we have perfect information. You have the Bernoulli newsvendor problem, which is the classical one. And then we have the different distributionally robust version. And here the improvements are not insane. It's the order of a few percent, but you have to think we get this few percent just by changing a little bit the decision, the optimal bit in electricity markets. There's only one parameter to tweak. It's the ball radius. And actually, I did a lot of experiment, and there's quite it's not very sensitive to your choice of the ball radius eventually. Good, but so now to conclude, I hope I gave you a nice introduction to these newsvendor problems and how we can use them in different ways today for electricity market, for renewables and electricity markets. Based on the work with Miguel and Jalan, I wanted to show you that it's quite straightforward to introduce decision rules. I mean, it's quite a bit of work, don't get me wrong, but it's not something that is technically crazy today, that a lot of people do prescriptive analytics and use these linear, non-linear decision rules. Then we can do it in an online learning framework, which is super important for electricity markets because the environment is very non-stationary. And then finally, I wanted to show you that we can also do it in the distributionally robust version. Because we might as well, if we can accept that we are not sure we can trust the forecast, I think it makes sense that we use this distributionally robust version so that we make better decisions. So thanks very much for your attention, and I'm very happy to take any question you would like to ask.
Thank you very much for your nice presentation, Pierre. And to the audience, if you have any questions, please let us know and we will give you the rights.
No questions?
I'm sure there will be questions. Yeah.
Everybody is a bit shy.
Yeah, that's what happens. So I guess you are right. Yeah. But I did enjoy very much the way that you put these decisions into the model. Okay, you see, takes. Okay, so Luis, if you would like to unmute, we will be very happy to give you the rights. Otherwise, Pierre can read the
I
question.
can read the question.
Yes,
Go
I
for it.
think. Okay, thank you for the presentation. It was really interesting. I think I'll need to watch it again to completely understand everything. But I was wondering if you recommend us some literature or some book about this topic to understand it better and step by step.
Yeah. So, I mean, in terms of books, there are not so many that you could use as a basis. The two nice books that I know, the first author is the same. His name is Juan Miguel Morales. One of the books was written with Antonio Conejo, and the other one with me and some other colleagues. So there are two different books. One is called Integrating Renewables in Electricity Market, and the other Decision Making Under Uncertainty. And I think they give you a very nice overview of all the challenges, including trading, right? So if you wanted to look for books, I think that would be the books I advise you to work with.
Okay, thank you for your answer and for the presentation.
No problem.
Thank you very much, Luis. Are there other questions from the audience? I think there are no more questions in the chat. So I think you gave a very, very clear talk.
Hopefully, the papers are available there. I'll share the slides. I mean, or people can see from the video. There are two papers on archive. I think they're open access anyway in the journals, but I gave the archive links. So people can just look at the papers also to see more details about the topic.
It's always very nice to bring together the decisions making with the data side. So thank you very much, Pierre. And
no problem.
I think we are about to close the online seminar series. So we are going to share some slides. So to the audience, so today, May 6 was the last talk of the online seminar series, Machine Learning Needs Mathematical Optimization. So you know that we have been running this since January 2021. So the talks are all available in our YouTube channel, and you also know that we have built a mailing list for people to receive news. So this is basically something that we did thanks to the funding of the European Union. So this is one of the deliverables of our Horizon 2020 RISE project. So RISE means that we have exchanges between academia and industry, the so-called secondments. And so just to give you an idea, we are receiving here at Copenhagen Business School a colleague from Repsol at the end of the week, and he will be staying with us for a month. Emilio at the University of Seville will be receiving a colleague in June from the Denmark Statistics, and you can see other secondments that we have had. So through this intersectoral collaboration, we have had also publications, and we have had other deliverables like PhD schools and other training events. So yes, as I said, we have a mailing list of more than 2,000 subscribers that we have built across all these years, with more than 90 countries in this mailing list. And what we did was to put all this recording of all these talks in our YouTube channel. And then you can see that we have gathered up to now more than 20,000 views, so showing basically the interest in these talks. So you can see that these talks are containing more than 100 speakers. So I'm pretty sure that there are some familiar faces over here. And remember that we had both senior speakers, but also what we call the young sessions, in which we had PhD students or, say, postdoctoral researchers presenting their research. So here you have a glance of all the young sections that we run. So now it's time to thank everybody. So we first start thanking our sponsors. So as I told you, the European Union gave funding to our project, but we would also like to thank Euro, who gave funding for promoting basically OR as a tool in artificial intelligence. And obviously, Emilio, Nuria, Thomas, and myself would like to thank our organizations, so Copenhagen Business School and Universidad de Sevilla, for the support that they have given to us. So we continue with the thanks to our junior team. So without them, we wouldn't have been able to do this. So this started in 2021. So with the help of Christina and Sinia, then Jasone came, and then Thomas, and then Nuria. So finally, I would like to thank the audience so that has come to the online sessions, but also all of you who would find it easier to watch the recording afterwards. And what we would like to let you know, and that this is the end, but it's also the beginning. So we will come back after the summer, and we will have more sessions. So we have already gathered quite a few senior speakers who have agreed to talk in our new event. The event will have a different name, but we can promise that the kind of senior speakers that we will be talking there are of the same caliber as the ones that we have had up to now. So please follow us in social media, or say in our mailing list, because we will be announcing this very soon. In the meantime, as I told you, we have our YouTube channel. So if you have missed talks, there are plenty of videos out there. So thank you, everybody who made this possible, the speakers, the organizers, the audience, and all our sponsors. And now we thought that maybe, if you don't mind, we take a picture together to show the audience from the last online seminar series. So it would be great if, so we see lots of friends. We really thank you for being here on a continuous basis. We started during the pandemic, and now we all went through it, and we are in 2024, which is very nice. Okay, so thank you so much for showing the camera. I think we can take a picture. And yes, so thank you, everybody. And please be in touch.
Thank you. Thank you. Thank you. Bye.
Thank you, Pierre. Thank you
My pleasure.
for making
Bye.
it
See you soon.
today.
Thank
No
you.
problem. See you.